Hello, I'm Norman Wildberger, and today we're going to investigate the three most important problems in linear algebra and how we solve them using row reduction. The most important problem in linear algebra, I've already told you about that, it's how to invert a linear system or a linear change of coordinates. This problem contains within it the subproblem of how to compute the solutions to a linear system of equations. The second most important problem, that of finding the eigenvalues and eigenvectors for a square matrix. Very important computational problem. And again, it rests on row reduction to find the eigenvectors given the eigenvalues. I've put a little star here because finding the eigenvalues, as we'll see, is actually quite a subtle issue that's finessed largely in many linear algebra courses. We'll have to say a little bit more about eigenvalues later, but for today we're just going to concentrate on the two-dimensional situation where things are reasonably straightforward. And our third most important problem, how does one calculate the determinant of a square matrix? So determinants are for us the algebraic embodiments of area in 2 dimensions or volumes in 3 dimensions. And we want to be able to calculate areas and volumes, and the determinant allows us to do that. And today we're going to see how row reduction gives us an alternate way of thinking about determinants. Alright, so our first problem is how to invert a linear system. Here we have x1, x2, and x3 as one set of variables, y1, y2, y3 as a second set of variables. And we've got y1, y2, y3 expressed as a linear combination of x1, x2, x3. And our job is to invert that. In other words, to write x1, x2, and x3 as a linear combination of y1, y2, y3. We set up the augmented matrix for this system. It's just as ordinary, except there's a y1, y2, and y3 on the right-hand side. We're going to row reduce that, starting with this pivot here and using it to eliminate the entries below it. So to get rid of this one here, we're going to take this row and subtract 1 times the first row, giving us 0, 4 minus 3 is 1, 3 minus 2 is 1, and y3 minus y1 is just y3 minus y1. Now we're going to take this matrix and we're going to swap the rows 2 and 3 to bring a 1 in that preferred position there. Then we're going to use that 1 as the new pivot entry and use it to eliminate the 3 below it. So the third equation minus 3 times the second equation. Well, that gives us on the right hand side y2 minus 3 times this, minus 3 times y3 plus 3 times y1. It's now in row echelon form. The leading entries are staggered to the right, and all the 0 rows are on the bottom, but there are no 0 rows. Now we're going to carry on, do back substitution. First of all, we're going to multiply by minus 1 to make that leading entry a 1. And then we're going to use this entry to eliminate the entries above it by adding multiples of this row to the rows above it. So there we've multiplied that third row by minus 1. And now adding this row to this row gives us, well, we just have to take this and we have to add this. And that's what we get. 2y1 plus y2 minus 2y3, the sum of these two. And to get rid of this 2 here, we'll just take 2 times this row and add it to this one, giving us 7y1, 2y2 minus 6y3. It's almost finished now. The only thing left to do is to use this leading entry to eliminate the 3 above it. So we're going to take this row here and subtract 3 times row number 2. The algebra is a little bit more involved because we have to take this expression and subtract 3 times this expression here. And that turns out to be y1 minus y2. You can check. Now it's in fully reduced row echelon form. We've solved our system. The answer is that x1 equals y1 minus y2, that x2 equals 2y1 plus y2 minus 2y3, and x3 equals minus 3y1 minus y2 plus 3y3. And so here I've recorded our final answer expressing x1, x2, and x3 in terms of y1, y2, and y3. Now you may have noticed that that was a little bit involved because on the right hand side we had to manipulate y1s, y2s, and y3s instead of just numbers. So here's a new idea. What we can do in this kind of problem is we can simplify it by introducing a separate column on the right hand side for each of the variables y1, y2, and y3. This means that instead of dealing with the expressions like this, we just deal with how many y1s there are, how many y2s there are, and how many y3s there are at every stage. So now this is a redoing of that problem that I did on the previous slide, but in terms of these more expanded augmented matrices. So this matrix here now replaces the first matrix that we had on the other slide. The first row, instead of having a y1, we have a 1 here representing, there's a 1 y1, 0 y2s, and 0 y3s. This is like the y1 column, this is the y2 column, and this is the y3 column. This way we can keep track of the y1s, y2s, and y3s separately by having a column for each of them, which means that we don't actually have to write the variables y1, y2, and y3 down. It's a clever little idea. So here I've just gone through exactly the same operations that I did on the previous slide. You can have a look through them. And we're just going through and performing row operations in the same way. So for example, the first operation is take this row here and subtract this row here. We'd get 1 minus 1 is 0, 4 minus 3 is 1, 3 minus 2 is 1, 0 minus 1 is minus 1, 0 minus 0, 1 minus 0 is 1. This represents the equation x2 plus x3 equals minus y1 plus y3. Alright, so we can go through exactly the same thing. We end up with a matrix like this, which represents exactly the same information that we started with here, that x1 equals y1 minus y2, that x2 equals 2y1 plus y2 minus 2y3, and that x3 equals minus 3y1 minus y2 plus 3y3. And what we've really done here in terms of matrix arithmetic is we found the inverse of a matrix. The original matrix of coefficients, if we call that A, then over here on the right hand side we've computed A inverse. So this is the matrix A that represents A times X equals Y, and this matrix represents A inverse times Y equals X. And in diagrammatic form what we've done is we've started with a sort of a super augmented matrix with the matrix A on the left hand side and the identity matrix on the right hand side. And we've row reduced it so that it's in fully reduced row echelon form with the identity matrix now finally on the left. And whatever's on the right is A inverse. So this is, in fact, a general method for finding the inverse of a matrix. So let's record this now in a theorem. That if A is a square invertible matrix, then to find its inverse, what we do is we start with this super augmented matrix, A on the left, the identity matrix on the right, and we row reduce that until we get the identity matrix on the left, and whatever is on the right is the inverse of the matrix A. So I remind you the identity matrix is just the matrix with 1s down the diagonal and 0s everywhere else. So a remark, for large matrices, in other words for matrices where the number of rows and columns is say bigger than 3, this method is better than using determinants. It's faster. For the 3 by 3 case, it's roughly about the same amount of work, whether you use the formula that I gave you for calculating the inverse of a matrix, or whether you use this method. Another remark is that if the matrix is not invertible, then this method, of course, can't work because you're not going to be able to find an inverse matrix. Not all matrices are invertible. But nevertheless, this method is still useful. It still gives us partial information, as we'll see later on. Right, so our fundamental problem of inverting a system or inverting a matrix, almost the same thing, is solved by row reduction using this method. So the second most important problem in linear algebra is finding the eigenvalues and eigenvectors of a square matrix. So let's suppose that A is an n by n matrix. Up to now we've been mostly concentrating on 2 by 2 matrices or 3 by 3 matrices, and so I suggest you think about one of those two cases. But in fact, what I'm saying now works for the general n by n case just as well. Here's the basic equation that defines eigenvalues and eigenvectors. We're looking for a vector v so that when you multiply it by the matrix A, it gets sent to itself times a scalar. So a vector v whose general direction does not change when you multiply by the matrix A. We insist that that vector be non-zero because otherwise the zero vector always satisfies that equation, which is not interesting. The vector v is called an eigenvector, and this scalar, the scaling factor, is called the eigenvalue. So when we analyze this situation, I've already explained, what we do first is we look for the eigenvalues. And the way we find the eigenvalues is by solving this equation, that the determinant of A minus lambda I equals 0. We rewrite this equation in the form A minus lambda times the identity times V equals 0. And if that has a solution which is non-zero, that determinant must be 0. And that's a polynomial equation in the unknown variable lambda, which is of degree n, the same size as the matrix. All right, so now we have a polynomial of degree n, and hopefully we can find its zeros. A polynomial of degree n typically has n zeros. So let's suppose that we've found n zeros, lambda 1 up to lambda n. Those are the eigenvalues for the matrix A. Then for each eigenvalue lambda I, what we do to find the eigenvector is we have to solve A minus lambda I times V equals 0. We need to find a vector v that satisfies that equation. Well, that's exactly a linear system like we've been talking about. In fact, it's rather a special kind of linear system. So it's much like AX equals B, but with the special case that B equals 0. The right-hand side is the 0 vector. That has a name in linear algebra. It's called the homogeneous case. So when the right-hand side of the system is 0. It's simpler than the general system. And so what we're doing here is just like the general system, except that instead of having a matrix A, we have A minus some multiple of the identity. So it means we have to subtract lambda I, one of these values, from all the diagonal elements, and then solve this system. Okay, that's something that we can do now with row reduction. So let's have a look at an example. Here's a 2 by 2 matrix A, 7 minus 4, 2, 1. Let's find its eigenvalues and its eigenvectors. The first thing that we do is we set up the characteristic equation. Determinant of A minus lambda times the identity. It just means that we subtract lambda from the diagonal elements. Now what's the determinant of a 2 by 2 matrix? It's this entry times this entry minus this entry times this entry. 7 minus lambda times 1 minus lambda minus minus 4 times 2. We expand this out here, we get lambda squared minus lambda minus 7 lambda for a total of minus 8 lambda. And 7 plus 8, 15. And that's a quadratic equation. And in this case, it factors pleasantly as lambda minus 3 times lambda minus 5. So there are two solutions, lambda equals 3 and lambda equals 5. Those are the eigenvalues. And we give them names. We'll say that lambda 1 equals 3 is, say, eigenvalue number 1, and lambda 2 equals 5, that's the second eigenvalue. Now for each of those eigenvalues, we're going to have to find an associated eigenvector. And for the first one, the eigenvalue is 3. So we look at A minus 3 times the identity times V1 equals 0. We want to solve that equation for V1. So we take the matrix A, and we have to subtract 3 times the identity. It means we have to subtract 3 from the diagonal elements. That one will become 4, and that one will become minus 2, and otherwise the matrix is as it is over there. So this is the system that we have to solve. There's A minus 3 times the identity. There's our unknown vector V1, which is of the form xy, say. Alright, that's a linear system, which has zeros on the right-hand side. So when we form the augmented matrix, the column of zeros on the right-hand side is a little bit unnecessary because it's always going to be 0. So we don't even bother writing that right-hand column. We'll just write this matrix of coefficients and we'll row reduce that. How do we do that? Well, it's not too hard in this case. We'll divide this row by 4 and we'll divide this row by 2 to simplify things. And then we'll use this entry to eliminate the one below it. We'll just take this row minus this row. The two rows are the same, so we get a row of zeros. You always get a row of zeros. Otherwise, you haven't done things correctly. So what's a solution to this system? Well, the system is x minus y equals 0. It's really the only constraint. Well, if x minus y equals 0, it means that x equals y, so the vector 1, 1 would work. If we followed our technical recipe, what we're going to do is we're going to look at the non-leading column, which is this second one, corresponding to y. We'll set y equal to a parameter, say lambda. And the first equation is x minus y equals 0, so x also equals lambda. And then our solution is xy equals lambda, lambda, a multiple of 1, 1. Eigenvectors are always scalable. You can multiply an eigenvector by a scalar. You still have an eigenvector. So 1, 1 is a fine eigenvector for the eigenvalue 3. For the second eigenvector, lambda 2 equals 5, we solve a similar system. A minus 5 times the identity times V2 equals 0. Here's A minus 5 times the identity. We just subtracted 5 from the diagonal elements now. We're going to row reduce this matrix. There it is there. I'll divide both rows by 2. The second row is just the same as the first row, so if we take this row and subtract that, we can get a row of zeros. And the second variable is a parameter, say lambda, and x minus 2y equals 0. So if y is lambda, then x will be 2 lambda. So the general solution is xy, or 2 lambda lambda, or lambda times 2, 1. And we get rid of the lambda because we only need one vector, any vector that's a solution. So 2, 1 is the simplest solution. So we have two eigenvectors corresponding to the two eigenvalues. And now we should check that we've done things right. How do we do that? Well, just take the matrix A and multiply it by 1, 1. So imagine 1, 1 here. What are you going to get? 7 minus 4, that would be 3. And 2 plus 1, that would be 3. So if we take the matrix A and we multiply it by this vector V, 1, we're going to get 3, 3, which is exactly 3 times that vector. On the other hand, if we multiply A by the vector 2, 1, so imagine 2, 1 there, we can get 14 minus 4, that's 10. And 4 plus 1, that's 5. So that's the vector 10, 5, which is exactly 5 times that vector. That's indeed the eigenvalue eigenvector equation. So there it is. Row reduction is the main tool. So to remind you of the physical meaning of the eigenvector equation, let's go back to the idea of a reflection in a line. So this is an example that I looked at already previously in lecture number 7. We had a reflection in this line here, so the usual coordinate system. The vector v1 will happen to be vector 1, 2. And there's a line through the origin with that direction. Let's call it L. And we're looking at the reflection sigma of L in that line. And back then we computed what the 2 by 2 matrix is that represents that reflection. It's this matrix right here with entries minus 3/5, 4/5, 4/5, 3/5. And I remind you that the way you can get that matrix is by asking yourself what happens to the two basis vectors when you perform the transformation. So the basis vector E1 goes, you can compute, to the vector minus 3/5, 4/5. It'll be a little bit this way, a little bit this way, vector somewhere up there. That's how you get the first column. And the second column is just the image of the second basis vector E2 under this reflection. So it'll be sent somewhere up there. That's the vector 4/5, 3/5. Now if you have a look at these two vectors, the vector 1, 2, which is in the direction of the line that we're reflecting in, and the perpendicular direction, v2, which is minus 2, 1. That's perpendicular to the line. If we apply the reflection sigma L to v1, geometrically you can see we're going to get v1 again, because reflecting in this line leaves this vector unchanged. And if we reflect v2, well, we're reflecting in this line, so this vector, which is perpendicular, is going to go to this vector exactly on the opposite side. In other words, negative it. So sigma L of v2 will be minus v2. And we recognize that here is an eigenvector equation. v1 is being sent to plus 1 times itself, and v2 is being sent to minus itself. So the eigenvectors of this matrix represent the direction of the line and its perpendicular direction. So let's analyze this situation now, pretending that we didn't know what this 2 by 2 matrix represented. Suppose somebody just came and gave us this 2 by 2 matrix and asked, what does this transformation do? One really good way of trying to tackle that is to find the eigenvalues and eigenvectors. So, what would we do if we were just given this matrix A? To find its eigenvalues and eigenvectors, first we find the eigenvalues by setting up the characteristic polynomial. So there's A minus lambda I. Just take the matrix and subtract lambda from the diagonal. There's the determinant. Expand it out. It simplifies to lambda squared minus 1, which factors as lambda minus 1, lambda plus 1. So there are two eigenvalues. One of them is 1, and one of them is minus 1. By the way, that corresponds to what we obtained earlier, right? Because here we did see that this was an eigenvector corresponding to plus 1, and this an eigenvector corresponding to minus 1. So this agrees with what we obtained earlier. But let's carry on now. We've found the eigenvalues. Let's find the eigenvectors using row reduction. So to find the eigenvectors, A minus lambda I times V equals 0. We start with the first eigenvalue, which is 1. So we need to take the matrix A and subtract 1 times the identity. It just means we have to subtract 1 along the diagonal, and that's what we get. So there's the matrix A minus the identity. We simplify it by multiplying by 5 and dividing by 4. So its rows are now minus 2, 1 and 2 minus 1. And row reducing it is very simple because we want to get rid of this 2. We'll just add this row to this row here, giving us 0, 0, which is good. We need to get 0, 0 to ensure that the matrix, in fact, is not invertible. Okay, the top row, divide by minus 2, it's 1 minus a half. Non-leading column there is y, so we set y equal to lambda, and then x equals plus 1/2 times lambda. There's the general solution, lambda of half and 1. And so we can choose any multiple lambda that we like. And for convenience, we'll let lambda equals 2 so that we get rid of that fraction. So there's our eigenvector, the vector 1, 2, which may sound familiar from our physical description of the transformation. Here's the same story with the second eigenvalue, lambda 2 equals minus 1. So here's a plus the identity now. There it is right there. Multiply the rows so that they're integer values. So multiplying by 5 and dividing by 2 here. And multiplying by 5 and dividing this one by 4. Then we take the second row, just subtract the first row, get row zeros. Set y equals to lambda and x equals minus 2 lambda. Then we get the solution v equals lambda times minus 2, 1. And a particular solution, v2 equals minus 2, 1. We recover that vector which is perpendicular to the direction of the line. So purely algebraically, we can deduce that this transformation fixes this vector and reflects this opposite direction. So geometrically, it is in fact a reflection in this line here. The two eigenvectors are perpendicular. So that's good. That illustrates, in the 2 by 2 case, this very powerful method for finding eigenvectors. Later on, we're going to look at the 3 by 3 case and higher, where it's very much the same kind of story. It's just that finding the eigenvalues becomes more complicated. Now let's have a look at our third problem of how to compute determinants. The third main computational problem in linear algebra is calculating determinants. Let me remind you what a determinant is, at least in the 2 by 2 and the 3 by 3 case, which is what we've looked at so far. A 2 by 2 matrix A, B, C, D, the determinant is this number A, D minus B, C. And I remind you that its significance is that, first of all, it corresponds to the area of a parallelogram formed by, say, the 2 columns of the matrix. Another important aspect of the determinant is that the matrix is invertible precisely when this determinant is non-zero. So the determinant is telling us whether the matrix has an inverse or not. For a 3 by 3 matrix, the formula is more complicated. It's, in terms of these 9 entries, it's this expression involving 6 terms with plus and minus signs. Each term is a product of 3 entries in the matrix, 1 from every row and 1 from every column. So for example, this one here, A times F times H, A, F, H, corresponding to 1 element in each row and 1 element from each column. And again, this number physically represents the volume of a parallelepiped. It's like a sort of slanted box, which has sides determined by these 3 vectors that are the columns of the matrix. And the determinant is non-zero precisely when the matrix is invertible. All right, so we can, of course, use these formulas to calculate the determinant in any given problem. But the difficulty with that is that, first of all, it's a little bit complicated to remember. You need to do a fair number of calculations. And worse, in the 4x4 or higher dimensional case, the formulas become a lot more complicated. So we're looking for an alternative way of computing a determinant, and row reduction gives it to us. To explain that, I need to remind you of a few properties of the determinant. First of all, the determinant of a matrix is unchanged if you add a multiple of one row to another. That's one of our elementary row operations. In fact, our first elementary row operation that we use when we're row reducing. The determinant is unchanged. If you swap two rows, any two rows, then the determinant changes sign. It's multiplied by -1. And if you multiply any given row by, say, a number lambda, then the determinant is also multiplied by lambda. These are the three basic operations that we use when we're performing row reduction, and these remarks tell us what happens to the determinant when we perform those row operations. So our strategy is to row reduce the matrix, keeping track of what is happening to the determinant and moving towards a row reduced matrix where we'll see that the determinant is easy to evaluate. So we need one more fact about the determinant. So the last fact we need about the determinant is that if the matrix is upper triangular, then its determinant is just the product of the diagonal entries. Upper triangular means that it's got zeros below the diagonal, below and to the left of the diagonal. So this is a 2x2 upper triangular matrix, and its determinant is AD minus BC. Well, that BC term will be 0, so it'll just be AD. In other words, the product of the diagonal elements. Here's a 3x3 upper triangular matrix. And of those 6 terms that are involved in the determinant, all of them except for AEI involve one of those zeros. Or to put it another way, the only way of choosing one non-zero element from each row and column is to choose that element from that column, and then that element from the second column, and then that element from the third column. So the determinant in this case is just the product A times E times I. In fact, that turns out to be the case also for a 4x4 or higher dimensional matrix. So our new strategy to compute the determinant is to start with our matrix that we're interested in, say A, row reduce it to an upper triangular form, let's say U, keeping track of whenever we have to swap two rows or whenever we multiplied a row by a scalar, because those two operations change the determinant. The operation that we do most of the time under row reduction, namely adding a multiple of one row to another, doesn't change the determinant, fortunately. So it's relatively uncommon for us to have to record these two operations. So we've row reduced A to U, and then we calculate the determinant of U because it's going to be in upper triangular form. So its determinant is just the product of the diagonal entries. Once we have the determinant of U, then we can calculate the determinant of A because we know what we had to do to get from the determinant of A to the determinant of U. So as an example, suppose we start with this 2x2 matrix here, 1, 5, 3, 4. Of course, it's easy to calculate its determinant, but suppose we're going to use this strategy. Let's just record its determinant. It's some unknown number, let's call it delta. So the first thing that we do is we row reduce it. We take the second row and subtract 3 times the first row. So 3 minus 3 times 1 is 0. 4 minus 3 times 5 is minus 11. That operation has not changed the determinant, so this matrix also has determinant delta. But this matrix, we know what its determinant is. It's the product of the diagonal elements, namely minus 11. So we can say that the determinant of the original matrix A, which was delta, is the determinant of this thing, which is 1 times minus 11, or minus 11. That's pretty simple, and of course we could have also just said it's 1 times 4 minus 5 times 3. But the point is that this method works much better for 3 by 3 and higher dimensional matrices. Let's have a look at one of those more complicated examples. So let's calculate a 3 by 3 determinant now using this method. Here is a matrix. We want to find its determinant. So I've copied the matrix there, and let's suppose that its determinant is delta. We're going to row reduce the matrix. First thing that we do is we take the second row and subtract 2 times the first row to make that a 0. And then this third row, add the first row to make that a 0. What's happened to the determinant is nothing, because we've only added multiples of one row to another. The determinant is now still delta. In other words, these two matrices have the same determinant. Now I'm going to row reduce a little bit more, and now we're in a little bit of a tricky spot, because these numbers aren't quite as pleasant as they usually are. Usually I arrange things so that there's a 1 conveniently there, which makes it easy to eliminate the thing below it. Here there's an 11 in that leading entry or pivot entry spot, and a 10 below it. So we'd like to use this 11 to get rid of the 10. Well, we could just take this row and subtract 10/11ths of this row, and we could do that, and that would be all right. But it would introduce some fractions. So suppose that we don't really like fractions that much. We prefer to work with integer arithmetic. I think many of you will share that feeling. So here's another strategy. We can make these two values the same by multiplying this row by 10 and multiplying this row by 11. That's what I've done. I've performed our third row operation. Multiply this row by 10, multiply this row by 11. What's happened to the determinant when I've done that? Well, multiplying this row by 10 means the determinant is also multiplied by 10. And multiplying this row by 11 means that the determinant again is multiplied by 11. So those two multiplications change the determinant by multiplying it by 10 times 11, or 110. So this new matrix has a determinant 110 times delta. Okay, but now I've got the situation where this entry is the same as this entry. So now the next row reduction step is easy. I'm just going to take row 3 and subtract row 2. So there's row 2 as it was, and row 3 minus row 2. This minus this is of course 0. This minus this, 90 minus 33, that's 57. And that operation hasn't changed the determinant, so it's still 110 times delta. And now I'm in a row echelon form. It's upper triangular. It's only zeros below that diagonal. So I know that the determinant of this thing is the product of the 3 diagonal elements. 1 times 110 times 57. And that's supposed to be equal to 110 times delta. So cancel the 110s, delta equals 57. And you can check by using the original formula for the determinant that that's the correct answer. So haven't we done a lot today? We've addressed the 3 main problems in linear algebra and shown how this powerful technique of row reduction helps us to actually concretely solve these problems. Now admittedly, we've restricted our attention to the 2 by 2 case or the 3 by 3 case. And so later on there will be more to say about this story when we want to go to higher dimensions. But already we are illustrating the power of this row reduction technique to solve the problems we want to solve. So now we have to have some exercises to let you practice applying this technique. Our first exercise: to solve the following systems using row reduction. Our second problem: calculating the inverse matrices using row reduction. 2 by 2, a 2 by 2, a 3 by 3 matrix, which is upper triangular. In fact, it's rather special upper triangular, just with 1s along the diagonal. more arbitrary 3 by 3 matrix. And here another upper triangular matrix with the entries over here which are variable instead of being particular numbers. So see if you can find the inverse of that in terms of A, B, and C. Our third exercise is calculating some eigenvalues and eigenvectors of just 2 by 2 matrices. So there's 3 2 by 2 matrices. This one happens to be upper triangular. This is a symmetric matrix. It looks the same on both sides of the diagonal. Here's a more arbitrary one. And here are some other examples where the matrices are a little bit more general. So it's of the form A, B, 0, C. A, B, B, A. You don't know what A, B, and C are. And the lower triangular, we don't always just deal with upper triangles, there's also lower triangular, matrix A, 0, B, C. And finally, a last exercise to compute some determinants using row reduction, a couple of 2 by 2s and a couple of 3 by 3s. Next time we are going to carry on with even more applications of row reduction to linear transformations and geometrical problems in 2- and 3-dimensional space. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.